Finding the power of a quotient. The power of a quotient rule of exponents. For any real numbers a and b and any integer n, the power of a quotient rule of exponents states the following. The base in parentheses is a fraction a divided by b to the power of n. So imagine the base of a has an exponent of 1 and the base of b has an exponent of 1. We would take n and multiply it by the 1 and n times the exponent for b, which would be 1, which would equal a to the nth power divided by b to the nth power. So for example 8, we're going to use the power of the quotient rule. We're going to simplify each of the following quotients as much as possible using the power of a quotient rule, and we're going to write answers with positive exponents. So the base, which is inside the parentheses, is a fraction, 4 over z to the 11th power, raised to the 3rd power. Now keep in mind that the 4 has an exponent of 1. So we're going to take 3 and multiply it by the exponent of 1, so we have a base of 4 to the power of 3. In a denominator we have a base of z as an exponent of 11, so 3 times 11, we have z to the power of 11 to the 3rd power. So we have 4 to the 3rd power, which becomes 64, because again, if we look at our calculator here, 4 raised to the 3rd power gives us 64, divided by z to the power of 11 times 3, which is equal to 64 over z to the power of 33. In part B, the base is p over q to the 3rd power with a exponent of 6. So p in the numerator has an exponent of 1, and the denominator q has an exponent of 3. So we have p to the power of 1 times 6, which is p to the 6th power. In the denominator we have q to the 3 to the power of 6. So again, we have p to the 1 times 6 over q to the power of 3 times 6, which is equal to p to the 6th divided by q to the 18th. Now, if you go back and look at the examples of a and b, we don't have any negative exponents, so there's nothing for us to do to make them positive. In part C, we have negative 1 divided by t squared, which is the base, raised to the power of 27. So in our numerator, we're going to have negative 1 to the power of 27 divided by t squared to the power of 27. So let's take a look at the numerator. So if we take negative 1 and we raise it to the power of 27, it's an odd exponent. So that means we're taking negative 1 and multiplying it 27 times. But since it's odd, that means we're going to end up with a negative 1. Now if that was a even exponent, then we would get a positive 1. So we have negative 1 divided by t to the power of 2 times 27. So we're going to get negative 1 over t to the 54th power. Okay, next, D. We have the base of j to the 3 times k to the negative 2 to the power of 4. Now, we can do this by first distributing the 4, or we can then rewrite k to the negative 2 as a positive exponent, so we can rewrite this to have j to the 3rd power in the numerator, and then k to the 2nd power being positive now, and a denominator raised to the 4th power. And then we have j to the 3rd power raised to the 4th power, divided by k squared raised to the 4th power. So therefore, j to the power of 3 times 4 becomes j to the 12th. In the denominator, we have k to the 2 times 4, which is k to the 8th, and we no longer have any negative exponents. In part E, we have m to the negative 2 times n to the negative 2 raised to the 3rd power. So since they both have negative exponents, we can take the reciprocal of both of them, and we're going to get 1 over m squared n squared, and those are now positive exponents, raised to the 3rd power. So now we're going to get 1 to the 3rd power, and then we're going to have the denominator m squared n squared to the 3rd power. Now 1 to the 3rd power is 1. We have m squared to the 3rd power, n squared to the 3rd power. So that becomes 1 over m to the power of 2 times 3 times n to the power of 2 times 3, which is equal to 1 over m to the 6th times n to the 6th.